Good morning. Here we are back in physics lab, and today's lab we're going to be using energy conservation. So in class we've been talking about energy conservation. We've talked about kinetic energy and gravitational potential energy, and we're going to use those along with a pendulum. So what we're going to do is we're going to measure the gravitational field. How many times have we measured the gravitational field so far this semester? But we're going to measure it in a very different manner. What we're going to do is we're going to set up what we call a simple pendulum. A simple pendulum has a mass concentrated at one location. It has a string of some sort, or a stick or something, and then it swings back and forth. So it's rotating back and forth along a circular path. So the length of the pendulum will be the radius of that circular motion as it swings back and forth. Now we've looked at examples of this in class, so go back to chapter 8 lectures, I'm going to guess is in there. What we did is we looked at gravitational potential energy. We said that for a pendulum, specifically a pendulum, swinging back and forth, something following a circular path, the easiest place to define zero potential energy is at the elevation of the center of the circle. So we're going to call this zero potential energy. Maybe I'll write that in. So we are going to say that the potential energy here is zero. Now as the pendulum swings back and forth, it never reaches that height. And that means that the pendulum swinging back and forth down here, and it's going to be in the region of where the potential energies will be negative. But what we saw in class was that's not such a big deal. What we can do is say that if the pendulum is swinging back and forth, then theta is varying. So the position of the pendulum keeps changing. But for any given value of theta, the distance from the 0 point down to where the pendulum is at that moment is given by r cosine theta. That's how much of an elevation drop we have. So that says the potential energies can be written as mg h, where h is r cosine theta, and we have to put a minus sign out front to remind ourselves we're in negative territory here. Now with the pendulum, the idea here is to pull the pendulum back some angle that we're going to start with and then let go, and then the pendulum is going to swing back and forth. Now we talked about this in class too, that using potential energy is really useful as far as telling us how fast are we traveling as a function of position. But using energy conservation is not always very direct in terms of how much time does it take. If you think in terms of the potential energy formulas, here's our kinetic energy. Here is a potential energy term. Here's a potential energy term. Nothing in there has time, at least not written as it is here. But what we're going to find in lab today is that there is a way to introduce time in. Now, it's a little complicated. You guys are not responsible for going through all the details of these derivations. I am going to include this with the notes for the lab on Canvas. So here is a derivation of going through and showing how to calculate what the period would be for a pendulum swinging back and forth. What's the period of oscillation? And that period of oscillation we can calculate using energy conservation. Now just to point out, in a few chapters, in chapter 14 I think it is, when we start looking at oscillations, we're going to come back and look at a pendulum, and we're going to get an approximate formula. But what we're doing today is, in some sense, it's the exact formula. It's not just an approximation. This is using energy conservation, an exact formula, assuming that the pendulum's not losing any energy as it swings back and forth. Now, as a pendulum swings back and forth, we're guessing, it's going to be losing mechanical energy. There's air resistance. The string is going to stretch out a little bit and come back. So what's going to happen is the string is going to heat up a little bit. The air around the pendulum is going to heat up a little bit as the pendulum makes its way through. But for today's lab, well, let's see which numbers are going to be more reliable and which ones might be less reliable in lab for the day. So first of all, we're going to measure the gravitational field of Earth in the lab room here at Laney College using the period of a simple pendulum. And here's how it's outlined. So we'll start with energy conservation. We'll say that I'm going to pull the pendulum back and then let go. Now, when I first pull it back, it's got a certain amount of gravitational potential energy given by mgr times cosine theta naught. So theta naught is going to be the angle that we start with. Now, if there's no loss of mechanical energy, if this pendulum swings back and forth without losing any energy to air resistance, or then it should swing back and forth between theta naught on one side and theta naught on the other side. So whatever angle we release it from, let's say we pull it back and release it from 40 degrees. Well, if there's no energy loss, energy conservation says it should swing back and forth. So that's something we can watch for in the setup. We can look and see, as this pendulum swings back and forth, is there any noticeable loss of, in terms of angle? You know, again, if we started at 40 degrees, it should sweep downwards, come back up, and does it reach 40 degrees on the other side? We'll take a look and see. In any case, at any later time, we can write the energy as some combination of potential energy and kinetic energy. So I wrote that as at any later time, at any other angle, we can write this as potential energy minus mgr cosine theta and the kinetic energy. Now that says that the speed, as this pendulum goes back and forth, the speed as a function of position is going to vary. You guys know this, right? If you're in a swing and you're swinging back and forth, you're going fastest at the bottom, and then you slow down and stop, and then you pick up speed, fastest at the bottom, slow down and stop. That's what that formula is keeping track of. So it depends on what angle we release from, and it depends on what the angle is as we swing back and forth. And using the formula, we can go through and get a measure of force for V. Now, this is all energy conservation. How do we bring time into it? How can we actually calculate how much time this is going to take? And so this part you should be familiar with. This stuff you got to know. That's just part of chapter 7 and 8. Here's the more detailed stuff. What we can do is we can say that, well, the velocity at any instant is given by ds dt. So here it is at some point, and during the next time interval of dt, it will travel a distance of ds, where ds is a length along the circular path. So ds is a circular path that can be written as big R times d theta. So this is something that I'm guessing maybe you've seen it in first semester, maybe it's in second semester physics, where second semester calculus, where you start working with ds, rewriting that in terms of r d theta. But in any case, that is a formula that we use a lot. So what we can do is say that the velocity is displacement, a little bit of displacement over a short interval of time. That displacement is given by r d theta. We can flip that around and say that the amount of time that goes by when the pendulum moves a distance of d theta in terms of an angle, the amount of time that takes is given by r d theta divided by how fast it's going. So that says now, if we take the period of oscillation of a pendulum, here is this pendulum swinging back and forth. The full cycle of the pendulum can easily be divided into 4 sections. It's kind of like we start here, and then 1/4 of the period is reaching the bottom. And then another 1/4 of the period is reaching the angle on the other side. And then one more 1/4 of the period brings us back to the bottom, and then the final 1/4 brings us back to where we started. So if we want to measure how much time it takes to go all the way over and all the way back, that can easily be broken down into 4 equal sized time intervals, again, assuming that the pendulum is not losing any mechanical energy along the way. So that's what we'll do, is we'll say that the entire period then would be taking this dt that we have right here. So this is the amount of time. I guess we could write it this way. So 4 times dt. Now I'm only going to integrate from 0 out to theta naught. And that would make 1/4 of the cycle. So that would be 1/4 of the period. Now if I multiply by 4, that will give me the full period. And that's what we want. We want a formula in terms of the full period, because we're going to set up a pendulum and we're going to let this thing oscillate back and forth, and the easiest thing to count would be how many times does it go over and back. Now, carrying out the integration requires us to take this formula of v. Now this is v squared, so first of all I got to square root all this. And when I put all that stuff in, now I took the theta dependence and left that inside the integral sign. It's got a square root on it. And then I factored, the rest of the stuff I factored out. There's a reason for doing this, and that's because this allows us to go in and separate out, I guess the 4r was from here, and the 1/2gr is coming from here. And then it's this next step where we've separated it out into what we call a correction factor, and then what we call the period for small angle. It turns out that when we have a pendulum swinging back and forth, if the angle is small, if the amplitude of the oscillations, if it's only like 5 or 10 degrees, then the formula simplifies down to this expression. 2 pi times r over g square root. And this is something we'll come back and derive in chapter 14. But since we did the very detailed energy conservation calculations, we have an additional correction factor. So what you can do is you can say, well, what would that correction factor look like? How different is the period going to be based on this additional factor? And so I'm calling the correction factor little f. I'm plugging that into this formula, and then I took that formula and solved for g. So I want to be able to use this formula in lab today, and so we used energy conservation very thoroughly. Again, we're assuming that there's no mechanical energy loss. We'll see how good of an approximation that is. And then what I did is I wrote in all the different angles that we're going to swing the pendulum back and forth. Now, 10 or 20 degrees, these are kind of small angle oscillations. We're going to take it all the way up to 90 and see if we can still get reliable measurements, even if the pendulum is swinging 90 degrees back and forth in either direction. Now the timing, since we're going to have to use a timer to find out how long these periods are, because that's what our formula says. It says that I need to measure the length of the string on the pendulum. I need to measure the period. Now, as far as the length needs to get measured from the kind of the pivot location. I don't think those lined up. Down to the center of the mass. So I'm going to bring that back to the center of mass and include that extra distance, whatever it is, to take it from the center here to the center of the circular motion. That's going to be r. And then the period, we're going to get that by timing. So we'll get out the stopwatches and we will time these periods. Now, if I time individual periods, that might not be as accurate as if I measure 10 at a time, maybe 5 or 10 periods at a time, and then divide, right? And we'll take a look at the setup here in just a minute. So we'll see how that works. But it could be that we're going to use 10 cycles. We could also back off and maybe use 5 cycles for some of the longer cycles that are going to be more reliable in any case. But we'll measure how much time it takes for 5 or 10 cycles, and then we'll calculate a period from that. So if 10 cycles takes 20 seconds, then the period is 2 seconds. So now the correction factor comes in right here, and I've got to take the correction factor and I have to square it. So now the correction factor, and I did, this is a difficult integral. And so as far as I know, there's no exact solution. So I solved it numerically using my calculator, my HP 15C calculator, and that's like from way back. In any case, I solved those integrals. Now I gotta go back and check this first one. This first one's got me a little concerned. I realize I have a 1.000 here, and I'm not sure if it went that small or not. Anyway, it's possible that the correction factor to 5 significant figures is just 1 on the first one, but I gotta go back and double check. That may look different in the notes. But these are the other correction factors, and what I'm seeing is that the periods do take longer. So if we go back to this, the period is going to be directly proportional to the correction factor. So at 20 degrees, the period is going to be, 6 thousandths times longer, 6 parts in 1,000, 6 parts per 1,000. But as we go to higher and higher angles, you can see by the time we get to 90 degrees, these oscillations of the pendulum take 18% more time. So if this is a correction factor with 18% and it gets squared, that's going to introduce 18 plus 18 would be 36. It could be a correction factor like 36%. So that's going to be really important for us. As we get to these larger angles, we are going to need to keep these correction factors for certain. One approach to the lab would be, let's just do small angle measurements. For many reasons, these are going to be probably our best, most reliable measurements, because what happens at higher angles, what I'm guessing is going to happen, is the pendulum could become kind of unstable. It's really just a string with a mass attached to it. So what happens at the higher angles is it tends to get less stable. Now what also happens as we go to larger and larger angles is things are happening faster, and the air resistance effects do start to come into play. And so at these larger angles, as we go to larger and larger angles, I'm going to say the measurements we get are less and less reliable. We'll see. We'll take a look at some of these and see what kind of difficulties we might run into. But by going up to these angles, so you might be saying, well, why are we going up to these high angles? And it's because it's fun, okay? So we want to see if we can really do this. These are probably the most reliable measurements, but we want to see what happens when we go to these larger and larger angles. Are they going to be reliable? We'll see. So what we would like to do is try a bunch of different, well, not too many, different masses and different lengths. Now, if you notice this, in the formulas, notice the correction factor is just a number, okay? But the period depends on the length of the string, and it depends on the gravitational field. A larger gravitational field will give you a shorter period. If we took this pendulum setup and we went to the moon, the pendulum would oscillate more slowly. If we go to Jupiter, then it's going to oscillate faster. So it's kind of interesting that the period of the pendulum's oscillation depends on the local gravitational field. So that's why this lab is going to enable us to go in and get a measurement of the gravitational field without really dropping anything. I guess the pendulum is being pulled back and forth by the gravitational field, and that's how we're going to get that measurement. So now we've got some masses. Here's a 100-gram mass, and here's a 200-gram mass, and here's a 500-gram mass. So I'm going to try those. There's a 1,000-gram object here too, but once you get up to those 80, 90 degrees, swinging back and forth, those feel a little dangerous. So I would feel better with students here doing those. In any case, I think I'm going to go with these three masses. Now what's interesting in the formula is the period doesn't depend on the mass. This is one of those situations where you ask two questions. Well, the first question is, are all the forces basically gravity? Is gravity the force driving this whole process? And you go, yeah, it is. The force that's driving this is mg sine theta. That's the force that's pulling this mass back towards the center. And then you say, well, if gravity is the force that's creating the acceleration that we're looking at least the one that's going back and forth, then the forces are proportional to the mass, and the inertia is also proportional to the mass, and those effects will cancel out. So one of the predictions from our formula, we'll see if this works also, is we're guessing that the mass won't make any difference. Okay? So if I go from 100 grams to 200 grams to 500 grams, if R is staying the same, then we're going to guess that we're going to get kind of the same numbers. Now it could be that the higher masses are more effective in pushing their way through air resistance. So there could be an air resistance effect going on here. In any case, let's try some different values of mass. I've got 1, 2, 300 here, but I actually don't have a 300-gram mass. I guess I could combine them. I think I'm going to do 1, 200, and 500. So, and then I have to write down the length. Now, I've written down 1 meter, but it's probably going to adjust. We'll probably get the string set up and then go back and measure. It doesn't have to be exactly 1 meter. And then from the formula right here, so this is the formula. This is where we're going to get the correction factors from. Plug the numbers in, and we should come up with a bunch of numbers for G. So we want to try this out fairly thoroughly and see what we end up with. So if you guys have any questions, again, the energy conservation stuff you should know. In fact, I think that's a homework problem or an example. Maybe it's an example we looked at in class. This stuff's pretty interesting, so if you're so inclined, go ahead and take a look through this. An example of using energy conservation to actually find times. How much time does it take for some kind of a process to occur? All right, again, questions, stop by, let me know. Let's move on and take a look at the setup. All right, so here's kind of what the setup looks like. What I've got is I've got the 500-gram object. I've attached it to a string. I think you can maybe see the string here. So I've set up a couple of posts, tried to make this secure so that it's not wobbling back and forth. So I'm trying to give it a good close attachment. And then I took the string, wrapped it around that top horizontal post, and taped that into place. And then here is the weight down here at the bottom. Now, one of the problems I did run into, as I found out as I go to heavier masses, the string stretches out. So it's ending up, an extra centimeter or two. So I'm not actually duplicating this with exactly the same length. As the masses go up, the length went up a bit too. I've got my timer set up here. So here's my timer ready to go. Here's my string and my scissors and my tape. Here are the weights that I've been using. Here are the meter sticks. So I got a meter stick and I've got a 2-meter stick to measure the distances. And then these are actually the data that I've collected. So here is the data right there. And so that will show up in the notes for the lab. So that's kind of the setup. Let me take a couple of videos. Let me show you what this thing looks like as it's in action, as it's swinging back and forth. So I have attached a protractor And so what I can do is I can pull the string back and I can kind of estimate what angle I'm at. I'm going to pull this back right now and just take a look, and so I can show you guys kind of, I'm not measuring the angle on this closely on this one, but let's say this is maybe at 50 degrees or something, so this is what it looks like. So it's kind of fun. Yeah, I want to keep the camera away from being hit. And so there it is, swinging back and forth. Now what we can do is we can come over as it swings back and forth, and what I can do is I want to count 10 cycles. So I'm going to wait until it's right at the beginning of one of the cycles here and start. Now it's happening 1 cycle, 2 cycles, 3, uh-oh, it hit the side, so I didn't get it quite centered. So I'm going to, oh, but maybe it centered itself. I'm going to stop and reset, and I'm going to try this again. Ready, and start. Oh, it hit again. So you can see the alignment, there's a bit of an issue. I'm going to stop and check the alignment. All right, it's looking pretty stable right now. I'm going to try this again. I'm going to start my timer now. 1, 2, 3, 4, 5. So I got 13.23 seconds. Yeah, it's gone sideways now, so it's a good thing I kept 5 cycles and didn't try for 10. But that's the idea. So 13.23 seconds for 5 cycles, and I can divide that number by 5, and that is going to, it's going to give me a period. Now, I do need to have an angle, so when I'm going in and doing these measurements, I'm actually paying attention with the protractor as I pull this back. Let me take a look. Let me look at some shorter strings. So this is actually the longest string that I use. You can see that we're getting pretty close to the floor here. Let me show you what some of the other string lengths look like. All right, right now we're at a length of somewhere around 150 centimeters. So here is my 2-meter stick, and what I can do is I can get this set up inside here. I'm going to pull this back. I'm going to measure to the pivot location. You know, where is this thing actually pivoting from? And then I can read this. It's coming in, it looks like it's around 155 centimeters, something like that. I've got the more careful measurement written down. And then I'll go back and, let's say we want something about here. So I'll cut that much length off. And we'll come in and we'll tie another, ooh, maybe this is shorter than I was expecting. When you cut stuff, it makes it shorter. So let me see if I can get a loop in here. Maybe I can. There. Okay. Thank you for your patience. So there's a loop, and let's say that I move on and I look at the 200 grams. So this is what the oscillations are looking like with the 200 grams. And let me check and make sure that's still in your field of view. All right. And so what we can do then is I can get out, I think the 1-meter stick is going to be enough. Now I did a set of measurements somewhere around 50 centimeters and a set around 1 meter. This is shorter. So this is about 80 centimeters. This is kind of in between. But you can see, once again, so let's see what this would look like. So I'm going to come up with my protractor. Now, the protractor I've got taped on here, and what that's doing is it's giving me a guide. Now, you can see this is a bit of a rough measurement, but I'm going to try 10 degrees. So, see that? Those are my best measurements. So sometimes, students think, well, is that even moving? And yeah, it's moving, and it's moving very reliably. So let me do this. I'm going to reset my phone reset my stopwatch. And here we go, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. 17.59 seconds for 10 oscillations. Now before, I think the periods were 2 point something seconds. With this shorter length, we are down to 1.76 seconds. I don't know if this is noticeable, but these oscillations are happening more rapidly. So the period has been reduced. And then we could go to even a shorter length. So maybe try this again. But this is what the measurements look like. So there were a lot of measurements on this. I'll cut this fairly short and see if we can get something that is noticeably shorter in terms of period. So there's a lot of data on this. So you'll have a lot of stuff to kind of sift through. All right, so here we are. Does that seem faster? It is. So if we measure the periods here, the periods are going to be shorter. Now there was a big issue that came up. We were very concerned with what happens at larger angles. For these small angles of 10 or 20 degrees, we can measure 10 periods easily. The swinging back and forth is pretty stable. But what happens when I get up to 50 or 60 degrees? And then what happens when I get up to 90? Now you can see if I get up to 80 or 90 degrees, take a look at the string. String's not really staying fixed in terms of its length. It's not as stable here. Well, that wasn't too bad. See, it jerks a little bit. That's going to have an effect. And then notice, try it one more time, even though I'm starting at like 90 degrees, it doesn't come back to 90 degrees, so it's a lot of mechanical energy loss going on. I mean, the amplitudes now are probably down to like 70 degrees. Although they're doing pretty well, it's staying around 70 degrees, it looks like. Okay, is my guess. So anyway, again, some of these, let's try it. Try something that's heavier. Now remember, our prediction was that the mass won't have much of an effect. Now, it's a little longer, so that's another thing to keep in mind here. So the string here isn't any longer, but the object is. So the object now is 40 centimeters out, whereas before, the object was at a shorter distance. So before, the object was 38. So the string is stretching. So the lengths are changing. I got all those lengths measured. Now again, as we swing back and forth at the larger angles, there's also the possibility that at the bottom, the tension's going to be larger. So that's where it's going the fastest. That's where we have the largest centripetal force, and the centripetal force is coming from the string. String's going to stretch out more as we go to higher angles because it's going back and forth faster and faster. So these are all things to think about, to be concerned with. They can certainly all be addressed in the limitations part of the lab report. So if you're always wondering what to put in the limitations part of the lab report, there's plenty of items here. Once we go up to those higher angles, the instabilities that happen, the loss of mechanical energy, we just can't keep this at, we're just not keeping this at 90 degrees as it oscillates back and forth. All right, I think that. So it's not very stable. The string, this is getting loose. Maybe with 500 grams we'll do better, although it seems a little dangerous. Yeah, so we started at a larger angle, and it's not too bad, the losses. We'll see. We'll run the numbers, take a look at the data, and run the numbers through and see what we have. And as always, whatever questions you guys have, stop by and we'll get questions looked at.